Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, maximum difference score in a grid. Because of the constraint of the problem can be solved either just using top-down solution and simulating whatever is given in the problem statement, or converting, you can optimize it further by converting this top-down solution to bottom-up and applying suffix sum. If you are someone who faced difficulty in converting top-down solution to bottom-up solution, or understanding why or when to convert top-down to bottom-up and why exactly bottom-up could help in certain scenarios, I am very sure by the end of this video you will be able to learn few new things that you can apply to any future problems that you see of similar pattern. So with that, let's get started. The problem states that we are given a m cross n matrix grid consisting of positive integers. You can move from a cell in matrix to any other cell that is either to the bottom or to the right. Now they may not be adjacent. The score of a move from cell with value c1 to a cell with value c2 is equals to c2 minus c1. Now you are free to start at any cell and you have to make at least one move. Now your task is to return the maximum total score you can achieve by making as many moves as possible. Notice you have to make at least one move. So if by making a move you are getting a negative value, that will be your score, right? So let's take an example. Let's say this is a matrix. Now you're free to choose your starting point. Let's assume that we are starting at this particular cell, which is 0, 1. Now from here you can jump to various places. You can jump to this cell or this cell or anything to the bottom, which is this cell or this cell or this cell. So for this sample, let's say you jumped from 5 to 7, right? This is a valid jump, and what is the score? Score would be 7 minus 5, which is 2. Now from this 7, again you can jump to anything to the right or anything to the bottom. So from 7, let's say you jump to 14, and the score would be 14 minus 7, which is 7. So overall, if you stop your journey here, so from starting from here till here, you made 2 jumps. First jump had a score of 2, second jump had a score of 7. So in total you got a score of 9. You can try out any other possible path. Let's say you start at 8 and go to 9 and then to some other cell, or any other possible path. You will not be able to accumulate a score greater than 9 with as many jumps as you want, and hence the answer here is 9. So hope the problem statement is clear. Now how to approach this? So first of all, we know that we are free to choose any possible cell as the starting point. So let's first of all, let's assume that you are doing something like this, like you are iterating over every possible starting cell and you are calling a function for every possible starting cell, and this function will give you what is the maximum score possible if you start at r comma c. And if you can implement this f of r comma c, you can simply do this. If you can simply call the function for every cell, and you will get the value if any cell r comma c is the starting point, and based on that you will just take the maximum across all of them and you will get your final answer, right? So what we need to do now is focus on how to figure out f of r comma c, that is starting at a cell r comma c, what is the maximum score I can achieve. This is what we need to compute. Let's assume this is the starting cell, right? Now from here let's try to make our first jump. Now from here we are allowed to jump to anything to the right or anything to the bottom. So this is a possible jump, this is another possible jump, and this is another possible jump. Similarly, this is one possible jump, this is another possible jump, and this is another possible valid jump, right? So from this you can jump to any of these 6 cells. Now let's assume that you have jumped to this cell. right? Let's try to figure out what will be the total maximum score possible if you make this as your first jump. Now from here, again, you can jump to this cell or this cell or anything to the bottom. Basically, you have to repeat the exact same thing. But think about it. How will you formulate this problem? This problem would be starting at here, starting at this cell, what is the maximum score I can obtain? Isn't this problem exactly equal to the original problem? And you can simply call the exact same function for this cell, and this will give you what is the maximum score possible if you start at this cell, right? And based on that, you can simply add whatever is the score of this jump, and you will get what is the maximum score possible starting at this cell if you make this jump as your first jump. In the same fashion, you can figure out starting at this cell, if I make this jump as my first jump, what is the total score possible by simply figuring out the score for this jump plus the total possible maximum score possible if I start at this particular cell. In the same fashion, I can figure out the value for this, and this, and I will just take the maximum across all of them to get the maximum total score possible if I start at here, right? So that's basically the algorithm. Now there's just one more catch here. The catch is you may not want to perform further jumps. For example, let's say you made this jump. Now you may perform this like from this cell, you may perform further jumps to any of the possible cell, or one of the alternative could be you stop here, right? So there are two possible choices for every cell you jumped to. Notice you have to make one jump at least. So one of these jumps would be required. Along these 6 arrows, you have to jump to one of these cells. Now after jumping is what we are trying to understand. After jumping, it is not required to jump. You can jump to increase your score if it is increasing, but it is not necessarily required to make another jump. So in that case, you can simply figure out the value of f of r comma c, where r comma c is this new cell, and if this is less than 0, notice it can be less than 0 because this, let's say this is the maximum value across all of the cells here. So whatever f of r comma c will get, it will be negative. So if it is negative, you don't want to decrease your score further. So you will not include it in your further calculations, right? So that's basically one small observation here. Like after making the first jump, you can choose to stop there and not go further, right? So for now, let's forget about that point, and let's look at one small example before we move further. Let's assume you are trying to find out f of 0, 0, which in turn means what is the maximum score possible if you start your journey from 0, 0. Now you have to make, if you are starting your journey from 0, 0, you have to make at least one move. So what would be the possible moves? Possible moves would be either 0, 1, 0, 2, 0, 3, 0, 4, or 1, 0, 1, 2, 1, 3. Sorry, 1, 0, 2, 0, 3, 0, 4, 0 is not there, so let's remove this too. Right? So these are the possible moves. Now with each of these moves, you have to figure out what is the total score possible if I make the move. So for example, let's say you are trying to find out what is the total score possible if you make this particular move, which is 0, 0 to 0, 2. If you make this move, what is the score? First of all, this move score would be 2 minus 2, which is 0. So to make this move, you incur a score of 0. Now what is the value of f of 0, 2? That you will figure out in the exact same fashion. You will consider this as your starting point, and from this you will go to all possible first iteration. Notice that f of 0, 2 means you are starting your journey from that cell. That is, you have to make at least one move. So either you will do any of these move, or you will not do any move at all. That is also possible because you finally want to compute the value of f of 0 comma 0. So either you call f of 0 comma 2, let's say you got x1 or x2. Now if x2 is less than 0, you will say, okay, why I will make the move and decrease my score. I will simply not make the move and keep the score 0. So that's basically how you will proceed. Based on whatever value you will get, the final answer would be the score from this first jump plus whatever score you are getting afterwards. So for example, let's say from this one f of 0 comma 0 to 0 comma 1, you are getting a score of 1 minus 2, which is minus 1. From this you are getting a score of 0. From this jump you will get a score of 0 again. Now from this jump you will get a score of 8 minus 2, which is 6. Similarly, from this jump you will get a score of minus 1 again. From this jump you will get a score of 0 and then again minus 1. So this is the scores if you make these all jumps. Now from each of these jumps, let's say you are getting x1, x2, x3, x4 and so on and so forth. So your total value would be x1 minus 1. If you make this particular jump, this will be your score. Similarly, x2 plus 0 will be the score if you make this jump. Similarly, x3 plus 0 will be the score, x4 plus 6 will be the score, and so on and so forth. And you will simply take maximum across all of them, and that will be your maximum score possible if you start your journey from 0 comma 0, right? So hope this entire thing is clear. If you are still not sure, I would encourage you to rewind the video, watch the past 5 minutes again, and do drive in with a pen and paper. That will help you understand this bit more better. Let's look at the pseudocode. The pseudocode is exactly what we have discussed. We will simply call f of r comma c for every possible starting point. And how to compute r comma c? You know the value of the bottommost cell, this cell, because from this cell you can't jump to any other cell. So if you reach here, it means the score starting at this cell would simply be minus infinity, because you can't make the first jump. And if you can't make the first jump, you can't, like, that is not a valid set of moves at all, because it is given in the problem that you have to make at least one move. So if you can't jump, basically that's not a valid jump, a valid move, and hence you will simply offset it by putting something like minus infinity. So this is kind of a base case. Now this will come to that. Now let's say you want to compute f of r comma c. So for that you will first go to all of the cell in the right in the same row, right, and then you will go to all of the cell in the bottom in the same column, compute their values and get the maximum across all of them, and that will be your answer. Now when you are going to the right, you also, like, what are the possible steps? Again, as we discussed, there are two possible choices. Because you have made the first move already, you can decide to stop there. So this is like if you just make one move, what is the score? Or you can say, okay, let me try moving further steps and see if that helps. So this is your multi-step move. So from this you will get this will be your score, c2 minus c1 basically, and from here c2 minus c1 is there, plus you are making some more moves by saying what is the maximum score possible if I start my journey from r comma right. Similarly with down, there are two choices. Either you will stop your journey in the first move itself, or you will continue your journey by saying that, okay, let me figure out what is the maximum total score possible if I just start my journey from this particular cell, right? So hope this entire pseudocode makes sense. Now coming to this part, this is the simple memorization part, because you can see we might need to compute same state again and again. For example, f of 0 comma 3 you needed to compute here, and f of 0 comma 3 is something you needed to compute here as well. In the same fashion, there will be other states as well, and if you expand f of 0 comma 3, there will be large tree beneath it. So instead of computing f of 0 comma 3 from scratch, you can simply store its value once you have computed that and reuse that value whenever asked. So that's what we are doing. Let's say we assumed everything, we stored -1 here. Again, -1 will not work because -1 is a valid value, so you will maybe fill it with -infinity or something of that sort. So you will fill it with some dummy value, and if that possible value is not the dummy value, it means you have computed that before, and you will simply return that particular value. And notice we are simply substituting the value after we have computed that particular state, right? So what is the overall time complexity of this entire algorithm? So let's figure out the complexity for f of r comma c, and then we will come to this loop. So first of all, we this is the recursive function with memorization. That is, you will be computing one state exactly once. If you have computed f of 0 comma 3 once, next time f of 0 comma 3 is asked, you will simply return from here. That's guaranteed, right? So for anything which is already stored, you will just require order 1 operation. So let's avoid that fully. We will simply care about the unique state computations. So how many states are there multiplied by what you are doing inside each of the state. So number of states would be number of different values of r multiplied by number of different values of c, which is equals to m cross n, right? Now inside each of these state, you are running two loops. First loop will go over all the columns in the right, second will go to all the cells in the bottom. So overall this can go up to m plus n times, right? And inside the loop you are doing some constant operations itself, so you can avoid that. So this is your overall time complexity for this particular function. Now it might look to you that okay, we are calling this function m into n times, so the entire complexity will be multiplied by m cross n again. But that's not true, because what you have computed here is the time complexity for computing every possible FRC, right? Now because every possible FRC is computed, when you call this FRC here, now you will be sure that you will hit this condition and you can simply return from here. So this FRC is not actually computing this entire thing again. Instead it is just an order 1 operation, so this mn will not be required, or rather this multiply would simply be a plus here, that is just order 1 operation, so we can avoid this entire thing completely. So overall complexity is simply m cross n multiplied by m plus n, and because of the constraint it will pass the given time constraint as well, because m plus n is 2000 and m cross n is 10 power 3. So it is very close to the time limit of 1 second usually. So depending on how you code, it may or may not pass. So if you do this thing twice, it may not pass, but if you can merge these two into a single one, it may pass. So that's what a valid, or this solution is particularly correct and also pass the given time constraint if you can code it efficiently. So next we're looking at the code for this, and before moving forward to the code, I would always encourage you to pause and try to code this entire thing by yourself. Only motive to look at the code from here would simply be you want to understand how to code this better, right? Not exactly you are not able to code and hence you want to look at the code, because if you're not able to code starting at here, it means you don't understand the problem in the first place. So next let's look at the code. The code is exactly what we discussed. We simply created this dp array and filled that in with -infinity. Now for all the possible starting point, we are simply calling max score of FRC. This max score function, you can think of it as f, right? Now this max score function, what we are doing inside this, we simply, this is the base case that we discussed. We'll simply look at if the score is computed already. If it is, we'll return that. If not, I will go to every right part and then every down part compute the maximum scores from each of the possible moves and return that as answer, right? So this is the overall solution, and this might pass the constraint depending on how you implement. So this exact solution will not pass. This was failing, I think, at the last test case, but I think you can simply merge these two parts by simply making this plus max of this comma 0, and I think this can go away and this might pass the given time constraint, right? So overall, I hope you understand this particular solution. If you have any doubts, feel free to post them in the comment section below. Next, let's try to optimize this solution. Now, how to optimize from here? So let's see the three factors in our time constraint, time complexity. One, m cross n. This is coming from the state itself, right? Now, if you want to remove one of these, it means you want to remove one of the states from here, which is a complex problem in itself, because what we are saying is whatever state you had previously, you wanted to remove one of them. So basically, whatever algorithm you have applied is something which you can't apply anymore. You have to think from fresh. So let's not focus on this part. Let's try to remove this instead. Now, where from this is coming? This is coming from the fact that we are iterating over every right and every down cell. Now, if you want to remove these two loops, that simply means you either don't want to iterate over every right and every down, or what you are doing inside the loop, you can do it without iterating, right? These are the two choices. So first statement, you don't need to iterate, is something which is not fully correct, because or rather it can be correct, but you then need to make some observation that, okay, starting from here, I may not need to go to all of them. Let's say I just go to one of them, and which one to go I can figure out efficiently. So that's that observation you need to make and prove it as well, that it is correct, because you are skipping most of the cells. So you need to prove that skipping those is always optimal. So that actually is hard. It's equivalent to proving a greedy solution, and proving a greedy solution in itself is sometimes hard. So we'll not go there. Instead, what we will check if we can do whatever this loop is doing in order one time, or rather this loop is trying to compute maximum across some of the states. Let's see if we can compute the maximum in order one time. Now, you can't compute this maximum in order one time because of this f. You don't know the value of f, so you can't run any range query data structures to compute this efficiently. And when you see this kind of constraint, that's a biggest hint that you might need to move to bottom up, because when you move to bottom up, this state is something you already have computed previously, and you will simply use dp of r comma right for that, right? And if you use that, you might be able to optimize with any range query data structure, right? So let's look at that. So first, let's convert this solution to bottom up, and then we will see how we can optimize this. Now, how to convert a top-down solution bottom up? That's very straightforward. We have discussed this multiple times in the channel. Let's look at it here. The simplest thing to do is just see what is your base case and see in which order you want to compute your state. So in this case, you had two state R and C. You just need to figure out what is the order in which you want to compute R and C. So in this case, you can see you know the value for the last cell. So what would be, let's say let's look at this grid 1. Let's say you know the value for this. Now, which cell you will know the value next? This cell or this cell, right? Because to know the value of this cell, you want to know the value of this cell as well. So basically, if you know the value of this cell, the value of this cell is something you can compute, because that only requires the value for this cell. Similarly, if you know the value of this cell, this cell value is something you can compute, because that also only required knowing the value of this cell. So basically you will go either in this fashion, or you will go either in this fashion. Both of them are equally correct, right? So that's exactly what you need to that's the only thing you need to decide, that in which order to compute the states into, and that you can get you can guess by intuitive fashion that you are computing everything backwards. So in this order you should compute RNC. Once you know about this, just copy paste the rest of the things from the bottom of top down solution itself, and this is a valid bottom up solution, right? Now let's focus on here and see how to optimize the complexity. Notice what we are doing here is taking maximum across grid of R of right minus grid of R of C, and then grid of R of right minus grid of R of C plus dp of R of right. So only this right is changing, right? So let's first focus on one of the expression. Let's focus on this expression only, right? What this expression denotes, this says that I want maximum over all possible grid of R of right minus grid of R of C. Now grid of R of C is constant for every possible grid of R of right. So for some time you can assume that this is not there, because this is constant, right? So this will not affect which one will give you the maximum value. So instead you can simply consider what is the maximum value across everything in the right, and that will be something you will subtracting grid of R of C to get what is the total maximum, what is the contribution of this particular expression after looping over everything in the right? So how to get this maximum? This is basically maximum of everything in the right, which you can do via a suffix maximum, right? So you can maintain a suffix maximum array and get this value efficiently, or remove this loop efficiently, right? Now we have we got rid of this with a suffix maximum array. So let's say you have a suffix maximum array sm. So you will simply check sm of R of C, which basically says everything to the right of C in the rth row is something you want, and based on that, whatever is the value here, you will simply subtract the value of grid of R comma C, and this will be your maximum value across all possible right thing, and you will simply do one maximum of answer. So you do answer is equals to maximum of answer comma this, and that will take care of doing this expression repeatedly over this loop. So you have removed this with a simple one line operation. In the same fashion, if you can remove this as well, this loop is not required at all. Now can you remove this? I would encourage you to pause and try to think for a moment. This is very similar to what we have done just now. So you can remove this as well with a similar trick. You can say grid of RC is constant. So let's forget about grid of RC for a moment, right? Now what you have is grid of R of right plus dp of R of right, and you want maximum across all of them, right? So you already know the grid of R of right, and because you have already computed dp of R of right for everything to the right, you already know dp of R of right as well. Now once you have computed dp of R of right and you already know the grid of R of right, you can simply sum them up and also take suffix maximum of that particular expression as well, right? So for example, let's just copy over this thing here. So let's assume that you, one second. So let's assume you are computing this particular cell, right? So for this particular cell, you want, first thing, maximum of all of grid of R of right. For that, you can simply maintain a suffix maximum, and that will give you the maximum across all these values, right? Now second, you need maximum of grid of R of right plus dp of R of right. So before you reach here, or rather if you reach here, it means you have already computed all of these values, right? Which in turn denotes that you can simply take this, like you already know the value of dp here, you already know the value of dp here, right? So when you know the value of dp here, you can simply sum it up with the grid of this. So you can simply say this will be the grid of rc plus the value of dp. Similarly, you can also say this is grid of rc plus value of dp, and in this fashion you can build a suffix maximum across this expression as well. Like as soon as you know the value, you will do the suffix maximum of this cell. Now after doing this, you will compute the value of this cell with, let's say, sum of this expression. Now once you know the value of dp here, you can again do suffix maximum of this cell by summing up g plus dp at this cell and getting the maximum with the next cell, and that will give you the suffix maximum at this cell as well, right? So with this logic, you can also compute the suffix maximum of dp grid of R of right plus dp of R of right, and once you have the suffix maximum, you can simply subtract grid of R of c, and that will give you the final value of all of this entire maximum expression when you run this entire loop. So again, this entire loop you can simply replace with a simple expression, which is, let's call it sm2, which is suffix maximum 2 across R of c, which basically says everything to the right. I want suffix maximum of the expression g of R of c plus dp of R of c, and you will simply subtract grid of R of c to that, and this will be your total value or maximum value across all this, and you will simply do one maximum with answer. So answer would be maximum of answer comma this. So you will replace the entire thing with this expression, which is just order 1. In the same fashion, you can do this thing for this as well. So overall, you need 4 suffix maximum array. 1 suffix maximum over the right, then suffix maximum over everything to the bottom, then suffix maximum of expression g plus dp from the right, suffix maximum of g plus dp from the bottom. And if you build these 4 suffix maximum array while you are doing these computations, you can easily get to remove this entire loop and get the value, right? So hope this entire thing is clear. Let's look at this one more time just to make things a bit more clear. So what we are saying is, assume this val is dp, right? So we are saying that dp of R of c would simply be maximum of all the grid values in the right and all the grid values in the bottom. So this you will get from one suffix array, this you will get from another suffix array. So this entire thing would simply be a number, this entire thing would be a number. So you are doing maximum of 2 numbers, which is order 1 operation, and just subtracting one number, again order 1 operation. So either dp would be this, like when you are just taking a single step, or when you are taking a multi-step, you also need to sum the dp value here, right? So again, this entire maximum you can get from a suffix maximum array. So this entire thing would simply be order 1. This entire thing would also be order 1 because you will get from suffix maximum array from the down. And finally, this would be you are subtracting this with grid of RC, which is also order 1. So you will do maximum across this, and that will be your final answer for dp of rc. Now once you get dp of rc, you will update these two suffix maximum array for r comma c. So suffix maximum array 2 of rc would be simply whatever value you got plus grid of rc. So let's say you got dp of rc as dp of rc, and let's say grid of rc is printed as grid of rc. So this is the value, current value. You want suffix maximum, so you will simply take this maximum with the sm2 of r of c plus 1, right? And whatever is the maximum, that will be the suffix maximum across everything in the right? In the same fashion, you can compute suffix maximum of down as well, with dp of rc and grid of rc, and suffix maximum of down with r plus 1 and c. So hope this entire solution is clear. If you have any doubts, I would encourage you to rewind the past 10 minutes and watch that again. I am intentionally not showing you the pseudo code for this because I really want you to go and try it out on pen and paper if you don't understand this part, because this kind of trick is very normal in certain DP problems, and I hope you understand when to convert from bottom up to top down, top down to bottom up, and how to leverage the bottom up solution itself. So notice that here you just had maximum, but let's say you wanted sum as well. That also you can do using suffix sum, or if you wanted, let's say, bitwise or something of that sort, that is also possible. So when you do a loop where everything is known, you can easily utilize any range query data structure to solve your problem. So that's where bottom up can sometimes comes handy. So next we'll be looking at the code. Again, before moving forward, I would strongly encourage you to pause and try to code this entire thing by yourself. So this is the code. The code is very straightforward. Now one small thing that I have done is, instead of maintaining two suffix array, one for grid of rc and one for this, I just maintained one suffix array where I just taken maximum across grid of rc and grid of rc plus dp of rc, because at the end I want to take maximum, so I just took that initially itself. So this is the dp array that we have been talking about, and this is the suffix maximum in the right, and this is the suffix maximum in the down. Now this is the suffix maximum of both grid of rc and grid of rc plus dp of rc, because at the end I want overall maximum. So first I will find out the value of dp of rc, because that is required to find out other two suffix maximum. So dp of rc would simply be either suffix maximum of right or suffix maximum of down. And notice, because these two contains both grid of rc and grid of rc plus dp of rc, you don't need 4 expressions here, rather 2 expressions would be fine. So you will take whichever is maximum minus grid of rc, right? Now this is the dp of rc. Now once you calculate dp of rc, other two you can compute very easily, which is, let's say, suffix max of right. So suffix max of right would simply be whatever is the suffix max of the next value and what is the current value. Now current value would simply be either this or this, right? Again, why both? Because we are not computing two different suffix maximum, we are just computing one suffix maximum, so I just taken both of them in the same suffix maximum. You can again, for simplicity, you can keep 4 different suffix maximum array, one with just grid, one with grid plus dp, and then same for the down array as well, and that will lead to the same thing, right? So because there is just one, I just got taken both of them in the same suffix maximum, and similarly for down you will do the exact same thing. It's just that you will take the next down suffix max instead of the next right suffix max. So after this entire thing, you will have the value of dp of rc for every cell, that is if you start at r comma c, what is the value? You will simply take the maximum across all of them to get your answer, and that will be your final answer, right? So hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I hope you are able to learn at least one new thing from the video. If you do, hit the like button and do share with your friends so that they can also learn this, learn something from this video. I will see you in the next one. Thank you.